since the Saros cycle can happen for, or over the course of 1,226 to 1,550 years or so. So in a single grouping of Saros cycles, of eclipses, there can be anywhere from 69 to 87 eclipses per series. So like I said, from the image we saw before, each eclipse every 18 years was moving a little further north from what we saw. So even numbered Saros cycles shift northward. And that's because it occurs that the moon is either going on an ascending node or a descending node where the eclipse occurs. And it's off, the draconic cycle is off by about an hour for each of those. Right? Pretty close, but off by a little bit. Draconic, to remind you, is where the moon hits that node. Which means that how the shadow of the moon is hitting the Earth is shifting just a little bit each time when it comes back around each 18 years. It's not perfect, but it's enough. So for Saros cycle 136, it starts off, we'll restart here in a second, for this even numbered one, which is for northern shifts there, near the descending node. It starts off with only partial eclipses hitting the very bottom of the Earth. And then over the course of the complete cycle, it starts moving up further northward, the path is changing, progressing further up until finally we only have partial eclipses at the top of the Earth, and then the shadow is missing us for the rest, and that is the end of that specific Saros series. And it's very predictable.
And what does the X represent?
Where's the what?
The X.
There's a green X that's going down the screen.
Oh, gotcha. I am not actually sure for that one. I found the GIF online. I did not make it myself. I can tell you that the sun, you can see the path of totality, which is that purple line from the sun across. There are multiple things visual in there, right? So we'll show you where you have to be for a partial eclipse, where you have to be for the total eclipse. There are times when we are close enough to a anomalistic cycle, where the moon is just on the edge of a certain point of perigee or apogee, that you can literally have both an annular and a total solar eclipse on the Earth. So hypothetically, if let's say that was the eclipse that's coming up this summer in August, here on the edge of, in Oregon, on the edge of that eclipse, where it first kind of hits landfall, we might see an annular eclipse. And then the moon's getting just a little bit closer, and it becomes a total eclipse over the middle of the US, and then becomes an annular eclipse by the end. Those are rare, but they do happen. So even number series shift northwards, odd number series shift southwards. This is only a small clumping of what's called the Saros Inex panorama. There's free things online where you can grab like the Excel sheet that categorizes, 60,000 eclipses? Pretty amazing. And you can see these patterns here. So for these, each vertical or each column is a Saros cycle. And you can see starting off here with partial eclipses, moving up into total eclipses and weird hybrids, and then partial eclipses as they leave. So each vertical step up or down is one 18-year Saros cycle. Moving off to the right is something else we haven't talked about yet called the Inex cycle. So I'm pronouncing it wrong, but I'm pretty sure it's Inex. We'll go with Inex cycle. And that's equal to 358 synodic months. So about 29 years less by 20 days. So it relates back to similar eclipses, but separated by 1/2 node. So if one eclipse started off at an ascending node, if you headed over to the next cycle, it would be at a descending node, but a very similar eclipse. So one might be in a northern hemisphere, and then you flip over to the other node, and that eclipse might be in the southern hemisphere, but should look very similar. So represented in this panorama, the vertical, or the columns, like I said, are the Saros cycles, and heading horizontally, the rows are the Inex cycles. So separated by years, very similar as they kind of move through, and then similar but opposite nodes every single time, which would make sense. You'd have an even numbered Saros cycle, which represents that sort of northward shift, and then an odd numbered, representing a southward shift. And you can see this spread out over millennia, forward and backwards at this point. It's a really intriguing thing to kind of visualize the data. And notice there's this general shift. I unfortunately don't have the large panorama which you can print out with very tiny font and have it span several feet. Maybe we'll get that for the planetarium at some point and take a look at all the upcoming solar eclipses. But the predictability to it is very high. So coming up sort of to the end of this here, there's some important ecliptic periods and changing cycles. So when we combine the Inuit cycles as well as the Saros cycles in different ways, we get intriguing patterns as well. So there's the heliotrope, which gives us geographic longitude at the central line of the eclipse. So those are similar over the course of a little over 1,700 years. I'm terrible with names, my apologies, but Accuratisima? I don't hear this very often pronounced because these are such long scale cycles that I just haven't had to say them. So you can go get a dictionary and go from there. My apologies. And that one is where the latitude then of the central line is very similar, where it first passes. And the horologia, say that one with confidence, it sounds right, for about 3,300 years is the time of the ecliptic conjunction is going to be similar. The last piece for this is our system, Earth, Moon, Sun, is not static. It is constantly changing. The eccentricity of the Earth's orbit around the Sun is decreasing over time. We're becoming even more circular. The same thing is happening with the Moon's orbit, as well as it's moving further away, like we just talked about. So that results in a change of our animalistic, draconic cycles, as well as our as well as the cyanotic as well. But that changes very slowly over time. So that means, here we've got several thousand years represented, it doesn't change by much, but it does shift just a little bit. So what if we put this into terms of the Saros cycles, which are anywhere from 69-ish, or I don't know, between 60 and 80 or so eclipses, that is actually shortening over time. So each Saros cycle is now going to become much shorter over the course of millennia, right? Astronomical time scale. But it's there, and we've been able to predict it very well. So I don't know if you've ever seen this before. If not, you should look it up. I still have a lot of research to do on it myself, but I kind of ran across it. Like I said, vaguely heard about this, probably some interesting YouTubes. But about 100 years ago, and the Antikythera, so correct me if that's terribly wrong, they unearthed this mechanism, which they have dated at this point back to about 205 BC. There's sort of a reproduction of it there on the right, but it's a combination of multiple gears that, when cranked out, will produce calculations. Sort of old school computer in a way. And one of the many things that it does, which there is a lot, is oddly enough, there are Saros cycles in this machine. And that's somebody's been keeping track at one point of tons of data of eclipses and position of the moon and the sun. Not surprisingly, because humans love patterns, right? They tell us when to harvest, when to move on nomadically and look for different herds of animals, when to start packing up for winter and preparing. So we survived because we tracked patterns and cycles. So if somebody was keeping an eye on the moon and the sun, it produced a very interesting machine for it. Intriguing. Off Greece somewhere. So, questions? Thank you very much for listening. Hope you enjoyed. That is Karen Nyberg, by the way. She was one of my personal favorite astronauts. When she releases her hair in space, she very much looks like a troll doll. And she has some wonderful videos on how do you wash your long hair in space. For another time. Any questions?
When you were showing the view from the moon of a lunar eclipse in progress, and it had the various color filters, what was the reason why the second one was blue? If the blue light gets scattered, would there be a point when enough of the atmosphere was between the sun and one more thing? No.
Yes, I mean, so it'd be very quick, most likely, but you would be able to see it. I know, like, I've seen footage from a sunset on the space station, and you can watch it kind of do this almost in reverse, admittedly not from that perspective, but you actually see that light. So it's kind of very much like this as it's scattered out in space. It'd be harder to see, but it's there.
So the light that is getting scattered when we are having a sunset is being scattered into that little band, and that's why you see it there. It's like when it's getting scattered out of our view, it's getting scattered out.
I think what this is representing is, mostly if we're talking about the sunlight entering into our atmosphere to kind of create the blue sky, we're talking about light that's coming in a bit more direct for us. And so it gets scattered out, kind of like the previous slide shows here. But more of the red and whatnot kind of penetrating through. That being said, over a long enough distance, the red color, the longer wavelengths, the red also gets scattered. So that's why you can have something at near infinity like look at clouds and they still can appear white from a long distance away. In terms of this, I think that these colors are being scattered off sort of a thinner part of the atmosphere and not actually even passing through towards the Earth. So you get less of that sort of diffraction of that light.
But it would seem to suggest that also then the reds and all the other ones were being somehow scattered away and filtered out of it, right? For it to have that bluish look.
Well, it's more like the red light is being bent more at that point. It's being refracted more than the blue.
The red light can make it through the atmosphere better than any of the longer wavelengths like blue or yellow. So that's why the red is on the inner part of that triangle and it's able to go through the atmosphere.
Yeah, I mean red is the longest of the wavelengths of the visual light.
Lower frequency.
Yeah. For now. Talk to you guys.
Is there some measure of how the recession axis affects any of this? I know that's on the order of like 26,000 years, so it'd be a lot larger than that.
Definitely. Yes, there are definitely cycles. So in fact, there are more predictive cycles than just these ones we talked about. But you're right, since that is something like on the order of a 20,000 year cycle plus, it's not represented in this, but there are longer term patterns that we do see. In fact, that's represented somewhat in the larger scale panorama that I can show. Since they've mapped that out to 60,000, you actually see.
If you like cut that, if you cut that into chunks, you see sort of like a periodicity sort of a pattern.
Yes.
On the order of like some 2,000 years.
Yes, you absolutely do. So here's the interesting piece. So if you extended this out, what's really interesting is this data, the rest of it actually dips down and comes back up over a very long scale of
Cut that next to that would be the next set.
Absolutely. Really pretty good. So there's more than just these scales. These are short-term astronomical scales, right, versus a medium scale 20,000 year. Yeah. Yeah. Yes, absolutely. So the light from the moon is also being refracted through atmosphere. That is an optical illusion because so that is an optical illusion relative to the moon. We can talk about it yourself, but I think yeah.
So a long time ago, we had a solar eclipse in Portland. So if I work back 36 years, was that 1981? Was that when it happened?
No, you have to go back 53 solar cycles, or 3 serocycles will get you back to 120 degrees, 120 degrees, 120 degrees. So 3 serocycles will bring you back to roughly the same geographic area. It will have shifted north a little bit, so if we were kind of towards the bottom of it, or south, depending on ascending or descending nodes, right? But we'll be back in the same area, but it'll have shifted by. So, yeah, there can still be some, remember we're on different cycles though, so there can be some that still pass through Portland, and then another, do the quick math in my head, 54 years? 54 years, 33 days, 34 days, it'll come back around to the same spot.
It's called the Eclipse era. Do you know anything about how exactly that works? Or like how it was used?
Sorry, which thing again?
It was on actually.
Antikythera? That sounds better. So exactly how it was used? We don't. I mean, we're still trying to date it and figure it out. And it's not, I'm by no means an expert in that whatsoever. It's more like I was searching through this and found like, I found the picture. Wikipedia did. It just seemed like this really intriguing thing, but they found that there is definitely serocycles, there's other lunar cycles inside of it. So I mean, that means they were tracking lunar cycles, distance to the moon, distance to the sun, different bits, as well as several other cycles in there. So right, we can create some interesting sort of like algebraic systems that will be predicted for this. And the piece I didn't talk about is, this is sort of brute force math for it, right, in a lot of ways. Like, okay, let's take a look at integer, like let's do the algebra for it, let's pump through it. Using this, we can go forward and back in time and predict where eclipses were. Now we've got computers which will do things very accurately and kind of track these bits and changing cycles over time. But this is exceptionally handy for the, finding these patterns that do not require large-scale like, differential equations to do, unless you want to get very, very detailed out in the future. Yeah, I mean, look up the Antikythera. Look that up. There's really cool things about it, and there's a lot of work being done. We're still learning, stuff about ancient knowledge. Not to say ancient knowledge is any better than current knowledge, Just they knew different things, and then we burned out the Library of Alexandria. Another copy. Over here.
I have to ask, is it correlate at all with Fibonacci numbers or any correlation with any of the numbers?
No, off the top of my head. Mathematicians in the room? Dead mathematicians in the room?
That'd be too amazing.
That would be, yeah, that would freak me
It would
out.
be amazing.
Excellent question. Start looking at the data and get back to me.
I'll let you know.
Thank you.
Are there any, like, is there anything going on with startup cycles where they repeat themselves, like a dead startup cycle that's come and gone? Another one comes and it's the same.
I mean, they're approximations,
pattern or,
they're always like moderate.
the same kind of shape and time.
Yeah, I'm thinking about that. Not that I uncovered in the research that I was doing for this, but that seems very plausible in a lot of ways. But the question is at that point, well, how similar does something have to be in order to be a repeating stereotype?
Yeah.
So I think there's enough variation that you'll never have two series that will be the same, especially that we have changing eccentricities, that the moon is moving further out. So all of the variables are constantly changing over time, and the moon's not getting closer again. That's all. Unless we, I don't know, build a wall, not sure bring it back or something. Too soon. Any other questions? Or join us over at Gino's for soda pop and chicken nuggets. Cool. Well, thank you very much for showing up.
Stuff like that.